Welcome back to session 2 of the EasySpin Academy 2020. In this session, we're going to look at the very basics that are needed to simulate EPR spectra, in particular the spin system and the interactions that we need to specify. Let's switch over to MATLAB and start a new file to explore. So the most important thing about a paramagnetic center or spin center is, of course, specifying what the electron spin is, how many unpaired electrons there are. In EasySpin, everything about the spin system is collected in a structure, and the most conventional name for it is cis. But you can name it any way you want. In order to give the electron spin, you just type cis dot uppercase S, and then you specify the electron spin quantum number. 1/2, for example, for a simple radical spin 1/2 particle. If you want to have a spin 5/2, just change this to 5/2. If you have a system of 2 coupled electron spins, for example, in a dinuclear metallic complex or a biradical, then you just make an array in square brackets with the 2 electron spin quantum numbers, 1/2 and 1/2, for example. You can put a comma in there, or you don't have to. Either way will work. So that is the basics of how you define an electron spin. Now the next thing that's important to specify is the G value or the G tensor of the radical or paramagnetic center. To do this, just type cis.g. And now you have several possibilities. You could, first of all, you could specify the full G tensor. And like every tensor, the G tensor comes with 3 principal values. And let's take an example here: 2.03, 2.04, and 2.2. This is a full, basically the full diagonal of a tensor. You can see the 3 numbers are different, and this symmetry is what we call a rhombic tensor. And the values here are typical for a copper complex. Sometimes the G tensor has higher symmetry. It might be axial, in which case the 2 first numbers are equal. Let's make an example here: 2.03, 2.03, 2.2. You don't have to write this out if it's axial. What you can do, you can just write 2.03, 2.2. In this case, EasySpin will know that the first principal value is both for the x and the y direction, and the third is for the z direction, right? Just like for the rhombic tensor was the x value, the y value, and the z value. If you have multiple electrons, like for example up here with 2 electron spins, you can give a G tensor for each electron spin separately. So cis.g equals, and then in square brackets, you first give the G tensor for the first electron. Let's say 2.0, 2.1, 2.2. That is the first row of the matrix. Then a semicolon, which starts the second row. And then you enter the G tensor for the second electron spin. Let's say 1.93, 1.93, and 1.99. Just some fictitious example here. Okay, you could also, for a single spin, you can give the full G tensor, because a full G tensor actually is a 3x3 matrix. And when we specify just 3 numbers, what we are saying is that the matrix is diagonal, and we're only giving the diagonal values. So instead of just giving the principal values, you might also going to give the full G tensor. cis.g equals, and now you could write 2.0300 for the first row, 0, 2.040 for the second row, and 0, 0, 2.2 for the third row. And if you look at this briefly, you see I'm highlighting this with my cursor keys, and then I'm gonna press F9 to evaluate this selection. You could also right-click on this, and then there's the first item in the pop-up menu that says evaluate selection. Or I think on Mac it's Shift F9. So if you run this, you can see the answer in a command window, and it plots out the 3x3 G tensor matrix that we've defined. So Basically, this way of entering information about tensors applies not only to the G-tensor, but also to all other tensors like hyperfine couplings and zero-field splittings, quadrupole couplings. So next, actually, let's look up where we can find help about how to specify these tensors. If you go to the EasySpin documentation, the second item in the basics section is called the spin system. And if you look in there, we'll see after initial quick examples, you will see a quick overview of what everything can be defined from spins, G-values, hyperfine, nuclear quadrupoles, zero-field splittings. There's high order operators. You can enter electron spin couplings if you have a multi-spin system. EasySpin, as of 6.0, also supports nuclear shielding tensors, so kind of NMR sigma tensors. It also supports nucleus-nucleus spin-spin couplings, and you can also model paramagnetic centers that have orbital angular momenta and include spin-orbit interaction. There's also broadenings and some information on non-equilibrium populations. But let's click, for example, on zero-field splittings. On zero-field splittings, the help tells you that the field name that we need to use is D, and then there's a D frame option. Okay, so let's go back. Go back here and see what we can do. So first, zero-field splittings are only shift energy levels if the spin is larger than 1/2. So the smallest one is a triplet. So let's call this triplet.s, and it's going to be 1. You see, I'm not using cis here. I can use any name I want to identify the spin center I'm interested in. So we triplet.s equals 1. And now let's define zero-field splittings. Triplet.d, that is a zero-field splitting parameter. And let's put the number into 2870. This is always in units of megahertz. That is the default choice for all spin Hamiltonian all parameters in EasySpin. So 2870 megahertz is about 2.8 gigahertz. And this is the zero-field splitting for the nitrogen vacancy center in diamond, which is a carbon-centered defect radical in a diamond lattice. So this will generate, specifies a tensor that's axially symmetric, a zero-field splitting tensor. Sometimes you might have a rhombic D tensor. And then you would specify two numbers, let's say 1300 and 260. So again, everything's in megahertz. The first number specifies the D value, and the second number specifies the E value. So basically this is D and E. And again, it's in megahertz, right? As you can see, what I tend to do, and I think it's good practice, is to always add a comment after the end of a number you give that contains the unit for that particular quantity. Any comments in MATLAB start with a percentage sign, and so whatever you type after the percentage sign is ignored by MATLAB, and it's only for your own reference. You could also write this out in a different way. You could, for example, say 1300 times, and then 1, 0.2. Now what this means is first you define an array, and then you multiply each element of the array by 1300. Okay, this is basically the form of D times 1 and then E over D. And it's again in megahertz. And it's E over D is a very useful, it's useful to specify this way because you know, if the zero-field splitting is very large, the spectra at X band typically only depend on E over D and not on D directly. Okay, and finally, you could specify just the rhombic, the three principal values of the D tensor. For example, 400, 200, -600. And again, this is in megahertz. The first value is the principal value along the X direction. Second value is along the Y direction. And the third value is along the Z direction. In this case, the zero-field splitting tensor principal values add up to 0, and we say that the tensor is traceless, but that doesn't have to be the case. And again, like for the G tensor, you could also specify a full D tensor. So that's the basics about zero-field splitting. The next thing we should briefly look at are electron-electron couplings. So let's write out a spin system that has two spins 1/2. So cis.s equals 1/2, 1/2. Now, if you want to include an exchange coupling between these two electron spins, just add cis.j, uppercase J. And you can specify the coupling in strength again in megahertz. So for example, 5. Again, I annotate this with the megahertz comment. If there is a dipolar coupling, so a through space magnetic coupling between these two electron spins, you can add that by typing cis.dip for dipolar coupling. And let's say it's 3 megahertz. You might also want to calculate the full coupling tensor, the principal values. You could, for example, say cis.ee equals, and then some j value, which we define. Let's define a j value separately and a dipolar value separately. You see, these values are just variables. They're not part of the spin system yet. But you can define them and then use them to build your spin system parameters. So j times 1, 1, 1. This will generate an array of three numbers that are equal to j. And then we can add cis.dip, actually just dip, times then 1, 1, minus 2. And this will construct the principal values of a dipolar coupling tensor. So this will be the full, this will be when you want to specify the full coupling tensor between two electron spins, which is a sum of the exchange coupling tensor and the dipolar coupling tensor. All right, what's the next thing? The next thing, we need to talk a little bit about nuclear spins. Right? A lot of chemical elements have magnetic isotopes, and you can look at that by typing isotopes. And so running this, or you can just type it directly in a command window. When you type this, it fires up a small tool that's part of EasySpin as well. It shows you a periodic table with all information about magnetic nuclei. For example, let's click on nitrogen. On nitrogen, you will see 2 entries in the table below. It's probably a little small for you to look at here in the live stream, but it will have an entry for nitrogen 14, which is a spin 1 nucleus, and an entry for nitrogen 15 with a spin 1/2 nucleus. It gives the nuclear G factors, which differ a little bit for these two isotopes. It will give you the resonance frequency at a given field, which you can modify here at the bottom. It also contains the nuclear quadrupole moment, if there is any, for nuclei that have a spin 1 or larger. And it gives the natural abundance. So for nitrogen, 99.6% is nitrogen 14, and 0.4% is nitrogen 15 in natural abundance. So that's a quick explorative table here. And now how to specify nuclei for a spin system for simulating an EPR spectrum. Well, you just add them to your spin system parameters. Cis dot, and now the field name after the dot is nukes. Uppercase N. Now, one important reminder here is that EasySpin is case sensitive, just like MATLAB. And so if you type lowercase n, like this here, EasySpin will not recognize this, and you might get a strange error message. So always make sure to check your spelling. In order to specify nucleus, all you need to do is make a character array or a string and type in the nuclear isotope. So quote 14N, quote closed. So this would specify just a 100% pure nitrogen 14 sample, which you might not have because typically you have a natural abundance mixture in your samples, right? Unless you do some isotope enrichment. To specify the natural abundance mixture, you type cis.nukes equals just n, and that will be the natural abundance. Now for nitrogen, that's probably a little bit exaggerated because we know that N15 only occurs with 0.4% abundance, and you probably will not observe it in the spectrum. because you don't have enough signal to noise. So in general, if you simulate a nitrogen spectrum, it is absolutely sufficient to just include N14. But that's not the case for other nuclei, for example, for copper. So cis.nukes equals copper will actually include the two isotopes. And I'm going here over to the command window and typing in isotopes. And then let's look at copper. Copper is here. Copper has two isotopes, 63 and 65, and they have 70% and 30% nuclear abundance. So if you have a copper spectrum, you always have to include both in a simulation. And the way to do this is just tell EasySpin you want a natural abundance mixture, which you get by just writing copper without any isotope prefix. If you have a pure isotope copper, for example, copper 63, you just add the 63 in front. Okay. If you need multiple nuclei, well, all you do is just concatenate them with commas. So let's say we have a radical that's centered on a nitrogen and has some couplings to some protons. We just make a comma-separated list. So this would be a nitrogen, comma, a proton, comma, and another proton. And if you, let's say you have a system that's coupled to 2 chlorine molecules, or 3, you would just write Cl, comma, Cl, comma, Cl. And chlorine is one other of these elements that has multiple isotopes with significant natural abundance. And now if you want to figure out how many different molecules that actually makes, you can use a command called isotopologues. Isotopologues. Which basically, this is an EasySpin function that generates for you all the combinations of all the isotopes that can exist in this molecule, and it calculates the associated natural abundances. So let's see what we get for just Cl for 2 chlorines. For 2 chlorines, if you run this, I'm selecting it and I'm pressing F9, we can see that we get a table, and it tells us there's a 57% abundance of a molecule with 37 chlorines, and there's an 18% abundance of a molecule with a 35 chlorine, a 37 chlorine, and so on and so forth. So there's a total of 4 isotopologues. Okay. So when you deal with these type of mixtures, natural abundance mixtures, EasySpin is automatically taking care of those. So as soon as you write Cl or copper or N, when you simulate an EPR spectrum, EasySpin will internally simulate all the different isotope spectra and add them together. So you don't have to worry about this at all. You can specify also non-natural isotope mixtures. Let's say you had some money, you bought some sulfur 33 or oxygen 17, and maybe it's only 80% enriched, right? Then you have to take care of 80% O17 and 20% O16 in your sample, and it will generate, at least 2 EPR spectra that always come together. You can do that as well. The syntax is a little more extended, and you can find that easily in the documentation. All right, so now we've got nuclear spins specified. Nuclear spins couple to electron spins via hyperfine coupling interaction. And to specify a hyperfine coupling, it's very simple. You use a field called cis.a, where the uppercase A stands for the hyperfine coupling tensor. And same for the G tensor, you can specify either just a single value, if you want to have it isotropic, right? You can specify 2 values, say 2500, if it's axial. And again, I'm adding the unit annotations. It's always in megahertz. Or you can specify the 3 principal values for any tensor. And here would be, for example, a rhombic tensor. 20, 30, and 100 megahertz. So it's also possible to specify the full A tensor, of course. And it's very analogous to the G tensor before. If you have multiple nuclei, you basically specify 1 hyperfine coupling tensor per row. So let's say we have a 63 copper and a 14N in our spin system. Then we have 2 hyperfine couplings. Let's say the copper is 20, 30, 400 megahertz. Then semicolon to just start the second row. And let's say -8, -5, and 20 megahertz. The first 3 numbers are for copper, and the second 3 numbers are for nitrogen. This is how this works. So we've had G tensors, D tensors, and hyperfine coupling tensors so far. If you're doing nuclear hyperfine spectroscopy, you're running ENDOR or ECM spectra, you might also need the nuclear quadrupole coupling. So nuclei that have a spin larger than 1/2, so they did spin 1, 3/2, and so on, they are non-spherical and they have they interact with their local electric field distribution, and that adds a term to the spin Hamiltonian that needs to be included in the simulation. And the field for the nuclear quadrupole coupling is called Q, uppercase Q. So sys.Q equals, and you could, for example, enter 0.7. That will be for E square QQ over H equals 0.7 megahertz. This E square QQ over H is the standard parameter that is used to specify nuclear quadrupole couplings. Now, if you want to have 2 nuclei, what you need to do is just again specify 2 rows with 2 different values. So this will be for 2 nuclei in megahertz as always. By convention, the second parameter for the quadrupole coupling besides E square QQ is eta, which is the rhombicity. And if you have that, you can specify that as well. So for example, 0.2 and 0.1, actually let's make this a little larger here. This here, if you give 2 numbers for 1 nucleus, then the first number would be the E square QQ over H, and the second number is the eta. And now the E square Q over H is in megahertz, but eta is just a number. Eta has no units. So this input is a little inconsistent with all the other tensors, but it's consistent with the dominant convention in the field, which we thought was more important than the consistency with the other tensors. But of course, you can also specify a full Q tensor. For example, you could say sys.Q equals -1.5, -0.8, and plus 2.3. This is in megahertz, and this will be the full tensor. Okay. So that kind of summarizes the most important fields that you need to specify in order to get a simulation started about your spin system. I encourage you now to look through the script of this session. Maybe start looking at one of the exercises that are interspersed with what I've shown you, and also look at the documentation for the spin system. And this concludes the second session of the EasySpin Academy, and I'll see you back in a little bit for session number 3, which starts in about 16 minutes. See you.